Hi, everyone. My name is Julien Maingard. I work for Fastly. I spent a lot of time working in the performance space before I moved over to a CDN that was highly performance-focused. So I am a little bit biased about making things fast. I realize that's not why everyone's here, but bear with me. I think there's definitely some worthwhile content in here. One of the things that I see a lot is the fact that APIs are there to make things accessible, but I think it's always in aid of making sure that the users have the best experience possible. Ultimately, that's why we're all here. The internet is difficult to use, and we're here to make things available to everyone as fast as possible. So I thought just going back and not to oversimplify things, a little brief history of APIs would be in order. I guess for me, the idea conceptually is that APIs have been part of how we communicate as a social species. Idioms, shorthand, contractions, you can see that the internet has created a lot of lovely ways that this is manifested. The idea is that anything that allows you to send a message to a recipient with the smallest payload possible under the assumption that context is available to the recipient already forms the very basis of an API. There is essentially a menu of requests that you can make, and if you reply in shorthand, the recipient has got an understanding of what it is that you're trying to say. So as communication systems and protocols evolved, we started developing. Development languages came about, software development occurred, and naturally the way that we communicate started to form within that as well. And really it was just a concept of efficiency in the face of scarce resources, how to get something from point A to point B as efficiently as possible. Formally, an API is a set of functions and procedures allowing the creation of applications that access the features or data of an operating system, application, or other device service. Internally, code and data structures began to mimic this kind of behavior, and this enabled distributed systems to emerge. You know, the more efficient we were with connecting points A and B, the further away we could put them. And as communication methods improved, we could do the same with greater distance, or a shorter distance and a faster performance. Then came the web, which drastically increased the use of distributed systems. And this also increased the complexity of things quite significantly. The rise of the thick client meant combining remote data sources with local context. A centralized processing platform could be used to integrate information from a variety of sources, and that could supply information to end devices or recipients with the local context of what that data needed to mean to them. Formally, this kind of started becoming more ubiquitous when Roy Fieldings published his Architectural Styles and Design of Network-Based Software Architectures in his dissertation in the year 2000. Not too long after that, February 7th, 2000, Salesforce.com officially launched, and this was an enterprise-class, web-based Salesforce automation as a Internet as a service. That's quite a mouthful. But seeing as they were the first, they could call it whatever they liked. This was an XML API, and it was part of Salesforce.com from day one. It basically gave the recipients of their information the ability to essentially just query the data that Salesforce kept centrally and format that in the output that they wanted. So very, very useful. November 2000, eBay launched their own API after that, and things rapidly became very, very normal for there to be a kind of menu-driven API interface for applications from there. Ubiquity in the net meant that a lot of people were designing their applications this way. It was efficient, it was fast, and everyone was better off for it, really. Again, this adds a level of complexity that does need to be managed. So what do they look like today? Most of you will have either be in the middle of designing something or maintaining something or looking for advice on how to build a really good API-based system at this conference. So just again as an overview, moving to the API-based model meant that instead of having a monolithic application at the center of everything and everyone having to make requests in and out of that, you now have a distributed model. Microservices has become a lot more of a normal model in today, and each of those has got a modular responsibility that can be created easily, adapted easily, and iterated easily. And these all in turn speak to various other services using things like APIs and messaging services. Generally, and this is not the same for everyone, but generally you will have some sort of API management in the front. The API management will control requests coming in for the information. That will essentially make requests onto further subsystems. Those will interrogate the backend systems, and it will reply up the chain again until the client has got their information. So what are the features of API management? What is it that these kind of API systems need to do? So this is a very basic list. I suspect there will be more or less than that, depending on what it is that you're trying to do. But really, fetching and mutating data, authentication, security policy enforcement, load balancing, quite essential. You need to tell it where to go, to which service. Cache management in some situations, dependency resolution, and in some cases, contract and SLA management. The key point that this is all trying to do is improve control, visibility, and speed. I tend to like to focus on that last one, but definitely control and visibility are also very important. The idea that you can create highly dynamic systems means that API management is critical to these. Cool. So the internet's fast enough. Great. We can all go home. But that's clearly not the case. We live in a world where the internet is basically a reliance to most people these days to get your product to the end user. The demands of the modern internet are increasing day by day. The minute that we make a better application or improve bandwidth and capacity and technology, we're immediately, how can we put more down the line so that we can get this to a person faster? So we're in a kind of evolutionary model that seems to be getting better year by year, but we're still faced with the constant requirement of it just never being quite good enough. So we evolve. 20% of end users will abandon a mobile site that takes longer than 3 seconds to load. I think there's a variation of this that occurs in most places. This is one research point that we did. But it's fair to say that slow performance really is an application killer. People are frustrated by slow performance and will go and use something else if they can't get it in time. APIs are lightweight, right? They're great. They go from point A to point B, but they're dynamic. The other problem with that is that they change very often. They're personalized content. And so you can't just reuse the same ones over and over and over again like you can an image or a banner or something like that. And frankly, the speed of light from Los Angeles to Auckland isn't getting any better. I think that's pretty much a constant in the universe. And our planet is big enough that getting a byte from point A to point B is still going to take a long time by human standards anyway. The other aspect is if you serve everything from your API gateway or directly from your application, there is a cost to that. The ability to scale that application becomes your responsibility. The cost of paying a third-party service that you buy off the shelf goes up. All of this can be resolved in some way through what I'm here to talk about today, which is API caching. You can cache your APIs. The general theory so far on content and information transmitted across the internet is it falls into two broad categories. One is static, the other one is dynamic. Static is stuff that doesn't change very often, pictures, JavaScript, templates, things like that. Dynamic is content that either changes very quickly or is personalized to a particular user. You don't want to serve one user's content to another user. That would be a very big problem. I would argue that there's a third type. Event-driven content is content that basically changes that does not change until an event or an action occurs that means that content must change. Fastly was started by someone who worked at wikia.com. That essentially had pages that needed to be cached for years at a time. And then once somebody made one update, the whole page needed to change instantly. It became very, very hard to navigate that with TTLs. You either had to guess how long a page should be fresh for. You would probably be wrong most of the time. You'd have to balance it between requesting too frequently or not frequently enough. If you requested too frequently, you use more resources than you need to. If you requested not frequently enough, you're serving old content. Once a change has been made, you're not serving the most up-to-date content. So event-driven content we define as content that changes once you have new information. Traditionally, this has been very, very hard to accomplish because the ability to invalidate content in a cache mechanism globally took longer than what event-driven content typically would be fresh for. So in the case of APIs, typically 5 seconds would be a fair amount to cache something for. Purging something in 5 seconds is a little bit harder. And how do you make sure that it is consistent across the world and is within the time that you need it? The idea here is that you can do this. Modern systems have caught up with this system. In particular, Fastly has a cache and invalidation mechanism which, at the 95th percentile, can invalidate content at 150 milliseconds globally. I say the 95th percentile because you can't invalidate anything globally in 150 milliseconds. The point is that within the appropriate user base, it's easy enough to do. So I'm going to walk through now very quickly about an example of how this works. And in this particular example, I've got an article with a comment system. So basically, somebody can read an article, post a comment on it, and add their voice to the material of the article. In this particular situation, an article has a one-to-many relationship with comments, in that an article can have many comments, and a comment has a many-to-one relationship with users. One user can have many comments across multiple articles, but the idea here is that they are constructed using this schema. Very simply, I've also got a list of API calls that you can make that will basically fetch, or the accessors. These are inherently cacheable requests, and mutators. These are things that change information or add information to the central data source. These are typically uncacheable, depending on the use case. But they fall very broadly into two categories. So the purge is really the thing that unlocks all of this, is the ability to say, when something changes, I want you to invalidate all the content that I require for this entire page to be fresh. So you have your page, you have your comment, and you have a user that made that comment. There are a couple of different scenarios here. One is that a comment has updated the page. So when you reload that page, you would like a new visiting user to see all of the comments and not miss the most recent ones. So in that case, and in this situation here, we're assuming the use of some sort of ORM or object relational model that basically translates what you have in your database to an HTTP format. So basically, this is a system that says, when my data changes, I would like you to perform these functions here, which includes Fastly purge for a comment. That can be the self.id, that can be the article ID, or the user ID. The idea is that you can either purge all of the comments, so that when the user comes back, they have to refetch all of the comments. There may be a user that has said something that they shouldn't have, and you would like to invalidate all of that user's comments in one go. That's also something you can do with this. The idea is that users are constantly getting the freshest content while still being able to maintain cache. So you're basically living the best of both worlds between keeping something in cache and getting it as soon as it's fresh. A little visual model here on how this works. So the first time a user visits, or anyone visits, the request goes to the edge. The edge does not have that content. We go and fetch it from the server. The server responds. This user now has this, and the edge has this content in cache. The next time somebody goes back, they visit, the content is in cache, so they get the cached content, which means that you've saved yourself a round trip to the origin, both for performance and for scalability. That's fantastic. At that point, a new comment is added, and you can see there that this triggers an event, which is a purge. Then after that, the user either refreshes their browser or another user comes along, and they get the fresh content again, and the process repeats. So this gives you an idea of how you can both keep something in state, but also get rid of it when it's no longer valid. So you can live the best of both worlds. There's a couple of ways to make sure that this works really efficiently. That's a very broad example, but the key thing here is to know the components to what you're trying to do. One of them is basically tell the CDN to cache in one particular way and tell the browser or the client to cache in a different way. So the CDN can be controlled using the surrogate control mechanism. That's very easy. Cache my API for a day. Because I also have the ability to invalidate on the CDN, I can be much more confident with the cache and how long it should be in cache for. With the browser, you're probably going to want to tell them not to cache because you have no control over how the browser evicts content. In which case, you would say, just don't cache, always go and fetch the most recent content. You can also pair this with kind of 304 models to say, if it's already the content that I have, then don't refetch it, just use what I have. But the general mechanisms already exist there. And this means that users, again, have consistently got the most up-to-date information. Combining this with something that Fastly can also offer, which is a tag-based purging option. Purging individual objects, while it's great in an example, methodologically can be a little bit cumbersome. If you have to try and purge everything out of a library of millions of objects, it can very quickly become cumbersome. So what you can do is at the CMS level or at the content ingest point level or at the API management level, have it add special values into a surrogate key header. The surrogate key header basically is a tag version that says this object belongs to these different groups. So this is a picture of the New York Times. That is what their page looks like. And as you can see on the left side there is, the right side, there is an image banner at the top. There's several articles and several images. And each of those have got an individual tag name. So being able to batch purge article 134 will clear that article out. So if there's a spelling mistake that needs to be changed or there is information that isn't correct, those can be kind of published really quickly and then corrected when we need to. If the image, if in the field the photographer gets a better image while they're at the scene, that can be re-uploaded and republished to show the better content. And the idea here is that by purging in batches, you can clear out entire swaths of content or APIs or types of systems at the same time and get users to refetch the fresh content immediately. This is a great efficiency, and it means that you have got a very fine-tuned control over everything that you're trying to do. Some examples of how users have used this quite well, I think typically these are very good examples. I think we're all looking for everyday examples of how conceptual items can be used in the wild. How can this actually help me? So as an example, the New York Times sends blanket alerts. There's 20 to 30 million push alerts in a single minute. This is something that alerts people to breaking news, to new information coming around. New York Times subscribers typically are very information hungry. So this tends to be a very infrastructure-heavy system. They use Fastly to mirror those alerts and take load off of their central systems and saves around $25,000 a month by putting Fastly in front of all its alerts APIs. And this is something that they would normally have had to serve from their origin. Now it's something they can just offload to cache, and when it's a different system, they can just purge it all, and it's gone. Nice and easy. Hotels Tonight uses a very cool geofencing system where they actually restrict requests to the database by understanding where the user's location is and adding that as contextual parameters when they perform a search. So by narrowing the search, they've improved the performance by a significant amount And Fastly can do that just by adding that context into their basic API queries. Boots also uses the GeoIP module to be able to understand where a user is and load balances them to the correct places. They also use a microservices architecture, so not only can they send them to the correct data center, but the correct location within the correct data center, because they have the ability to understand context within each request, but they can also enrich that context through information that Fastly has available. So these are a couple of ways that APIs can be used in combination with cache and in the wild that can really make huge performance impacts to applications. Thank you very much.